Hello everyone, and welcome to another lecture on line commutated and PWM rectifiers. And today we will be talking about space vectors, a little bit of space vector PWM, and how we can control the voltage source converter when using space vector PWM. So basically we are now going into this part of the lecture here, which I have marked, and we are going to basically talk about these space vector concepts regarding to the PWM rectifier or PWM converter. And by the end of this lecture, you should be able to understand how a VSC is controlled using space vector PWM. There is one thing that is remaining in lecture as part of this one, lecture or week 3, hysteresis control, but we will take it up as we progress with the Clark and Parkes transformation. We'll take it up. Okay, now this is the content which is going to be covered today. I will not cover very much in detail about space vector PWM because we would like to more emphasize on the use of the space vector PWM for grid connected VSC. So more details, this I have another lecture series in NPTEL, which is called the high power converters and multi-level converters. So that lecture series has a much more detailed explanation of space vector PWM, and I would like you to refer to that in conjunction or along with this lecture, okay, to get a better understanding. So at first we will first understand what is space vectors. Okay, so the origin of the space vector concept lies with a rotating MMF in machines. So what do we do in rotating MMF concept is that we would like to express the resultant MMF of three-phase quantities by a rotating MMF. For example, if you have a balanced three-phase sinusoidal supply given to the stator winding of a three-phase induction motor, then you will see that the resultant MMF produced is rotating in space. So basically, what is this resultant MMF? It is a effect or a contribution of the three phases working together and giving a single quantity which has a particular direction and a speed and a certain angle with the reference, right? So space vectors also have a similar property, which means that space vectors also have magnitudes and a particular direction at every instant of time. Okay, however, the difference between space vector and the MMF concept in induction motors is that space vector is a mathematical concept. Okay, of course, when you talk about space vectors, it will be very useful for you to visualize it. Okay, and that visualization can be obtained from the rotating MMF concept. However, space vector is a mathematical concept which is basically used to show the effect of the three-phase variables in space. Okay, we would like to see the effect of three-phase quantities together by a single quantity, and that single quantity is the space vector. Again, it is a mathematical expression. And how does this mathematical expression look like? As you can see, the resultant space vector for any three-phase quantity, suppose we take a load phase voltage. So these load phase voltages A phase, B phase and C phase, these are shown here. Okay, these are instantaneous quantities of, say, load phase voltage, and the resultant space vector of this load phase voltage is given by this formula VRT, okay, which is 2 by 3. This is a multiplying factor, and then you have VANT, VBN e to the power j 2 pi by 3 and VCNT e to the power j 4 pi by 3. Okay, so we see that there is these three quantities VAN, VBN and VCN are combined together in this expression to form the resultant. Okay, the resultant has both magnitude as well as a direction. Okay, so it's a vector. And secondly, we also note that this resultant is a function of time. So which means that the space vectors are defined both at steady state as well as at transient operations. So it can change at every instant of time. Okay, this is unlike phasors. Phasors are only applicable at steady state. Okay, but space vectors can be equally applied both at steady state as well as at transient operation of, say, VSC. Now there is one more thing that needs attention, is this 2/3 factor. Okay, so this 2/3 factor is used because we want to make the resultant having the same magnitude as the A phase peak. So if you can recall the rotating MMF concept, in the rotating MMF concept, if you recall, in a machine, the resultant MMF is having a magnitude of 1.5 times, right? 1.5 times or 3/2 times the peak of the A phase quantity. Since it is balanced, so peak of A phase also means the amplitude of B and C phases are also same. But this 1.5 was coming, okay? That means the 3/2. So that is why we have used the 2/3 factor, and that makes it this transformation magnitude invariant, which means the resultant space vector, suppose if it is given, so if A phase is given by VA equal to VM sine omega t, okay, then the magnitude of the resultant vector will also be equal to VM. Okay, so it will be same magnitude, and that is because we have this 2/3 factor which is coming here. Okay, if we had not used that, then this will be 3/2 or 1.5 times. Okay, so this is something to be noted. Now, as I told you, space vectors are a mathematical quantity and can be used for any three-phase quantity. So we can define space vector for load phase voltage, but we can also define space vector of current. Okay, so space vector of current is like this: IRT, resultant space vector, 2/3 IAT plus IBT, and like that. Okay, and so space vectors can be used for many quantities. Okay, it can be used for grid voltage. So you can have grid voltage space vector, you can have converter voltage space vector, you can have grid current space vector. In fact, you can have machine stator flux space vector, rotor flux space vector, because any three-phase quantities can be represented by a single space vector which describes the magnitude as well as the direction of the, or magnitude and angle of the vector. Okay, the other point to note is that the space vectors, as per the definition, is the equation that we have described. It is equally applicable for both balanced and unbalanced operation, and these quantities need not to be sinusoidal. So which means that even in unbalanced operation, space vectors can be used, and we can find out what is the resultant space vector, and even in presence of harmonics also. So in presence of harmonics, what will happen is the space vectors will have harmonic components. So there will be a fundamental space vector and some harmonic components, which when you do the DQ transformation, it will come out to be, say, some ripples over the fundamental. Anyway, we'll talk about it later. So this is the concept of space vector. Okay, so this is the mathematical concept of the space vector. Now, how do I visualize it? Okay, so in order to visualize it, let us take a simple case. Okay, the sinusoidal three-phase currents. Okay, we take three sinusoidal currents which are given by IA, IB and IC, right here. and we would like to know what is the resultant current space vector. We would like to know. Now let us take some few instants. For example, you take this first instant at omega t equal to 0. What is happening here is that you have the A phase axis here, A, B axis here, and C axis here, and at this omega t equal to 0, which I have drawn here, you see that IA is 1 and IB and IC are minus half here at this point. So on this IA axis, on this A axis, I have drawn IA of 1 magnitude, and on the B and C phase axis, so IB is equal to minus half, so this is now drawn in this way, and IC is minus half, so it is drawn on the other way. Remember, this is the here is the A, B and C axis, right? So IA, IB, IC are drawn with IA equal to 1, IB equal to minus half, and IC equal to minus half. So when you do the vector addition of these quantities, what you get? You get the resultant space vector IR here. And you can understand that if you apply that the multiplying factor 2 by 3 as before, then the peak of IR and the peak of IA, they will be having the same value. Okay, IR is equal to IA, right? So this happens at omega t equal to 0. Now let us take any other time instant. Okay, suppose you take another time instant omega t equal to pi by 3. What happens then? So at omega t equal to pi by 3, you have IA as half here, and IB and IC, sorry, IB is again half, and IC is minus 1. Okay, so what happens here? IA is half here, and IB and IB is also half, so IB is half, and IC is minus 1. Okay, and therefore the resultant space vector comes here. So we can understand now that as the as the three phase quantities take up different values with respect to time, the space vector is basically rotating. Just like what happens in a rotating MMF, the space vector is also rotating. It has a fixed maximum amplitude of IR, okay, and it is rotating at the speed of omega and in an anti-clockwise direction. You can as well then go on with other time instants and can see that as the time progresses, the space vector is basically, so we can say that this is the resultant space vector, and the resultant space vector is rotating in time, and it has a circular trajectory, okay, because the peak is constant. This is the peak and it is moving like this, right here. Okay, so this dotted part I will remove. Okay, so IR is a circular, it is having the same at the fixed amplitude, and is rotating in a circular anti-clockwise direction, having the same amplitude, okay, at a uniform speed and constant radius. Okay, so now how do we now relate this space vector? So we have now understood what is the space vector concept. Now let us relate this space vector to the converter. Okay, so we have drawn this converter, and we would like to see the converter phase voltage space vector for different switching combination of the converter. Okay, now here what we are trying to see here is that first of all, you have to understand that this converter, this is the voltage source converter. This converter, if you take any one phase of the converter, it has two switching states which are given by 1 and 0. Okay, so you see here there are two, the top switch and the bottom switch here. Okay, so when you turn on the top switch, then VAO is equal to VD, which is denoted by 1 here, and otherwise if you turn on the lower switch, VAO is 0, which is denoted by 0 here. Okay, so this is that 1 and 0. Okay, so this 1 and 0 are the two switching states of the one leg of the voltage source converter. Of course, therefore, this converter has total 8 switching states because you have 3 phases and each of these phase can have 2 switching states. So in total, you have 8 switching states. Okay, what are these values? These values are 0, 0, 0. 0, 0, 0 means you are turning on all the lower switches, and 1, 1, 1 means you have turned on all the upper switches. And of course, then you have the 6 combinations of 1, 0, 0, 1, 1, 0 like this. Okay, so these basically indicate the switching combination. In total, you can have, for this voltage source converter, you can have 8 switching combinations. Okay, now out of these 8 switching combinations, these two combinations, which are 0, 0, 0 and 1, 1, 1, they are called zero vectors, because when you use this switching combination, the net voltage output from the converter is 0. Okay, right? Because of course 0, 0, 0 means you are not producing any voltage, or 1, 1, 1 means it's a balanced and not, so you don't produce any voltage. So therefore these are called the zero vectors. Okay, the 2 zero vectors. The rest 6, these 6 vectors, okay, these six switching combinations are called 6 active. Okay, 6 active, they will produce 6 active vectors. Okay, what are these active vectors and how do they look like? That is what we will see. Okay, so basically what we are trying to see is that for any switching combination, what is the converter phase voltage space vector? Okay, now we are trying to relate space vectors with converter switching state. Okay, so for what is the converter phase voltage? Converter phase voltage is this voltage VAN. VAN is the VBN and VCN. These are the converted phase voltages. These are the 3 quantities. Okay, right? So VAN, VBN and VCN is this converter phase voltages. Okay, this is coming across, so this is the filter. Okay, so this is the filter impedance Z. We can take it on R plus JX here, and then you have the grid here. Okay, here is the grid. So this is a grid connected VSC, and the converter phase voltages have been shown here. Now we are trying to understand what is the converter phase voltage space vector for a switching combination of 1, 0, 0. Okay, so let us see that. So when you say 1, 0, 0, 1, 0, 0 means VAO is 1, which means it will be VD. VBO will be 0, which means it will be 0, and VCO will be 0, which means it will be 0, right? So these are the pole voltages. 1, 0, 0 means VD 0, 0. So therefore VAOT is VD, VBO is 0, and VCO is 0. And this is how this is the O point here. Okay, VAO is this voltage, VBO this one, and here with respect to this voltage here. Okay, now what is there for VAN? Okay, this is the converter phase voltage, A phase. Okay, and this we have derived in a previous lecture, will be equal to 2/3 VAO minus 1/3 VBO minus 1/3 VCO. Okay, you have to recap from your previous lecture, and this is the expression of VAN. Okay, the converter phase voltage. And so if you substitute these values here, VBO this value here and VCO this value here, then what you see is that VAN is 2/3 VD. Okay, similarly you can also find out the B phase converted phase voltage, the value, and it will come out to be minus 1/3 VD, and VCN it comes out to be minus 1/3 VD, right? So once you have got VAN, VBN and VCN, then you find out what is the resultant converter phase voltage space vector, VRT. Okay, and this we have already seen the formula, and if you insert it, then at this time instant you see that we with this switching combination, you see that we get a VRT which is 2/3 VD at an angle of 0 degree. E to the power J0 means at an angle of 0 degree. So we say that the converter phase voltage space vector for 100 switching combination of the voltage source converter at a certain time instant will give me this space vector 2/3 VD at an angle of 0 degree, right? Now similarly, we can actually do this exercise for all the other switching combinations. There are total 6 active switching combinations and 2 zero combinations. Okay, so if you take the 6 active combinations, for example, you have this 1 1 0 0 1 0 and so on, which we will be using at some other time instance, right? So if you use that, so then you can make this table here. Okay, and what does this table show? That if you use a switching state combination of 1 0 0, which we have just derived in the previous slide, you get this value of 2/3 VD at an angle 0. Similarly, if you use 1 1 0 or 0 1 0 or 0 1 1, you will see that the resultant space vector, okay, 2/3 VD at an angle, say this is 60 degree, pi by 3. Similarly, 120 degree, 2/3 VD at an angle 160. And these are all these active vectors. Okay, they are producing a resultant vector which has a certain magnitude at a certain angle. And we find that as expected, we have the magnitude to be equal. Okay, here the magnitudes are all equal, right? So for all the 6 active vectors, the magnitude is equal, and for the 0 vectors, right, these two, the magnitudes are 0. Okay, so these two switching states 0 0 0 and 1 1 1, they will be producing 0 resultant space vector, but all the other 6 will produce a certain magnitude of space vector which has a certain magnitude, but the angles will go on changing here. Okay, the angles are changing. Now these are actually named. Okay, these are given some numbers. As you can see here, the 2 0 vectors are given V0 and V7 numbering, and V1 to V6 are given for the 6 active vectors. Okay, so this is how the space vector is related to the 8 switching combinations of the VSC, and we can find out what are the resultant converter phase voltage space vector. Instead of doing this mathematically, you can also do it graphically. Okay, you can quickly find out how the resultant space vector looks like. So for example, you can see here, this is the A phase and this is the B phase and C axis. This is the A axis, B axis and C axis. And suppose you have this 1 0 0 combination, you can say that the VR, okay, on the A axis you have this VR coming, and B and C axis do not produce any voltages because its magnitude is 0. Okay, right? So therefore the resultant magnitude is 2/3 VD, which is on the A axis. Okay, similarly you can take any other combination. Say you take 0 1 0. 0 1 0 means A phase has no contribution, C phase has no contribution, but B phase has a contribution of VD. Okay, and therefore the resultant space vector is along the B axis. Okay, this is the resultant space vector which is along the B axis here. This is the B axis, and it will be having this magnitude of 2/3 VD. So therefore it is not always necessary to go with the mathematical treatment. You can also visualize how the space vectors are being rotated. Okay, as you take up different combinations, you can understand that as you move from here to here, or from here to here, or from here to here, basically what is happening is this resultant space vector, this fellow here, it is jumping. Okay, it is jumping from this position to this position, from this position it is jumping to this position, and then to this position and this position and this position here. So it is jumping from so from here to here, and like here, 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 and here. Okay, right? So it is jumping on these on the space vectors, right? On this plane. Okay, now this one, therefore we can actually visualize in a much better way, okay, with the help of what is called as space vector diagram, and this is what we are going to talk now. So this is the space vector diagram. Okay, what is this space vector diagram? This diagram is the visual representation of the space vectors, and it is useful finally to visualize the whole thing on a plane. Okay, and we'll see how this is done. Okay, here you can see that the same thing that I had done in the in this table, whatever we had done in the table, I am now just depicting it on the space vector plane in the space vector diagram. And you can see here, these are the switching combinations 1 0 0 or 1 1 0 or 0 1 0, and the resultant, this thing, the V1, V2, V3, V4, all these resultants are now plotted. Okay, and this is the tip of the space vector. When you have 1 0 0 combination or 1 1 0 combination, okay, this is the tip of the vector. Okay, now sometimes we also use this notation. Okay, it's the same notation, plus plus minus, plus plus minus, or plus minus minus. It is the same notation. Some authors use this kind of a notation, while some authors use this 1 0 combination. So for example, plus minus minus means, okay, plus minus minus means that okay, this yeah, so plus minus minus means this is Vd by 2 minus Vd by 2 and minus Vd by 2. Okay, and this 1 0 0, okay, it also means the same thing. It is Vd 0 0, only the common mode changes. Okay, so in some cases we take the reference as the midpoint of the DC link, and in some other cases we take as the whole of the DC link. But you don't have to worry much about it. Let us continue with our convention of this 1 0 0 and 1 1 0 and 0 1 0. This strategy, let us go ahead with it. Okay, so with this switching combinations, we say that we have now the 6 active vectors which are shown here, and there are 2 0 vectors at this point, okay, which has this 0 0 0 and 1 1 1, and these are the 2 0 vectors, V0 and V7, having the 0 magnitude. Now with this space vector which are there, we can always draw an imaginary boundary. So this is the imaginary boundary which is connecting, okay, which is connecting the tip of the vectors, right? And this definitely will look like a hexagon. Okay, so this is the hexagonal space vector diagram, okay, in which there are 6 active vectors and 2 0 vectors, right? So yeah, now further to that, we can actually divide this space vector diagram into 6 sectors. Okay, and these sectors are numbered in the diagram shown. You have sector 1, sector 2, sector 3, sector 4, sector 5, and sector 6. Okay, so this is the total, what we called as the space vector diagram. Okay, and on this diagram we will be doing our analysis. It is very easy if you visualize this on the diagram. Okay, so which is shown in the this slide here. So you can see here, I have tried to portray the space vectors onto the diagram and trying to make you understand what happens here. So suppose you have this converter. So this is the converter here, okay, which is connected to the grid here. So this is the grid, 3-phase grid, and through a filter, and this filter has an impedance of say X. Okay, the resistive part of the filter, it's a L filter, RL filter, okay, or it's inductive filter. The R part of that filter is negligible. Okay, so you have just a simple X here. Now the converter voltage space vector can be adjusted to exchange certain P and Q with the grid, right? So this is what we have been saying even before also, that we would like to exchange a certain P and Q with the grid. Now if you remember, in some of the previous slides we talked about how the phasors can be adjusted, right? In one of the previous classes we said how the phasors are being adjusted so as to exchange a certain P and Q with the grid. Taking a clue from that concept, we can even also here say that the space vectors, now we are drawing in space vectors. So here you see the space vectors. Okay, so we are drawing three space vectors here: the converter voltage, the grid voltage, and the grid current. Okay, the grid current is following this way, I grid. And we can write down the space vector equation. So V conv minus J I grid X, so this is the V conv voltage, okay, minus J I grid X is equal to V grid, right? So V grid is here, this is the plus here, this is plus, so V grid is, so this is the space vector. So therefore we can say that V conv equal to V grid plus J I grid X, right? So therefore if this is V grid and JIX is will be this one, so it will be like this. Okay, so this is the JI grid X, right? So JI grid X, so this is the, so therefore you can see that how we are drawing the three space vectors. So we have drawn three space vectors on this diagram. So this is the first space vector, I grid, V grid, and V conv. Okay, very similar to the phasors at steady state. Okay, so but the space vectors we can actually draw it, this diagram can be applicable, is also applicable at transient also. Okay, so now we see that how we have drawn this on the space vector plane. Okay, V converter, the grid space vector, grid voltage space vector, and the grid current space vector. Okay, now of course what we can do here is and all of them, as you can see here, these are rotating. Okay, these are rotating in an anti-clockwise direction. Now in order to change the P and Q, what we can do is we can quickly change V conv. Okay, we can forward it, we can rotate it clockwise, anti-clockwise, and even we can increase or decrease the magnitude of this V conv, right? Once we play around with this V conv voltage, which is in our hand, remember the converter phase voltage space vector is in our hand, and the grid voltage is not our control, and the current is a dependent variable between the grid voltage and the converter voltage. Okay, so the converter voltage space vector is something which we can change, or we can increase, decrease its magnitude, or we can rotate clockwise, anti-clockwise, like that. And this can be done using the switching combinations, as I have already told. Okay, so this V conv is something which is in our hand, and we would like to manipulate this one. Now how do we manipulate it? And you can see here this diagram, on this diagram you see the imaginary boundary of the space vector. So imaginary boundary is shown in light color. Okay, you can see here this, there is the boundary of the space vector right here, and it is shown in this light color. And now what we are doing here is we are basically manipulating V conv. Okay, so remember here there is V1, there is V2, and there is V0 here. Okay, these are active vectors available to us. Okay, these are active vectors which are available to us, right? And by changing the duty cycle or changing the time duration for which these active vectors are used, I can actually manipulate vconv. Okay, I can make vconv going this way, I can make the vconv coming this way, or I can make the vconv smaller. Okay, as you can understand now that it is possible for me to continuously manipulate or adjust this vconv space vector. This is the space vector we will adjust. When we do that, what happens? Of course, the I grid will change, right? Because the grid, this v grid is constant. Okay, so if you manipulate vconv, I grid will change. Okay, it will change its position, and which will cause p and q to change. So you can understand that by manipulating the vconv, which we have also discussed when we discussed with the in the phasor, that by changing that vconv phasor, I can change the p and q. Similarly, with space vectors also we can do the same thing. Okay, but now this vconv change will be done using by changing the time durations for which these active vectors v1, v2 and v0 will be used, and this is what is known as space vector PWM. Okay, how we calculate the timings of v1, v2 and v0. So now we will see about space vector PWM. As you have seen in this slide, that we can control the V converter voltage, and to manipulate this V converter voltage we have to use V1, V2 and V0, these active vectors, right? Now what is the exact time duration for these active vectors and the zero vectors, to so that the correct voltage means the reference voltage or the vconv, correct voltage here means vconv voltage, how we can accurately impress that voltage, or how we can get that voltage from the converter. Okay, so this is again what I had said is called the space vector PWM, which is again an extension of sine triangle PWM, and but the timing here is done using space vectors. I'll not go in very much details of space vector PWM because the subject itself has been researched very thoroughly. Okay, and there is this my old lecture in NPTEL which is given in this link, and you can click on this and you will be taken to this space vector PWM. But I will not go into very details of the space vector PWM. I will just briefly mention about how this space vector PWM is done. So as I told you, we are trying to generate that vconv or the v resultant, okay, vectors, and we are going to use the three nearest vectors which is enclosing these reference vectors. These are the three vectors v1, v2 and v0. Okay, v0 and v7. These three vectors we will use to come to this point vr. Okay, so these vectors v1, v2 and v0 have to be used for certain time duration in a switching cycle to produce the resultant vector. So as you can understand, suppose and this formula is given here. Okay, this is the VRTS. Okay, VRTS is v1 vector for time duration t1, v2 vector for time duration t2 and v0 vector for time duration t0. Okay, so VRTS equal to v1 t1 plus v2 t2 plus v0 t0. So which means that in this triangle, okay, in this triangle we are trying to come to this resultant vector by switching the three nearest enclosing vectors v1, v2 and v0 with these timing durations t1, t2 and t0. Okay, so basically what does this mean? It means that this resultant vector is nothing but v1 plus t0 plus v2 into t2 by ts plus V0 into T0 by Ts, right? So what does this mean is that these are as if like the weights, okay, these are weights to be put on the three active vectors. More is the weight, okay, but remember that Ts is equal to T1 plus T2 plus T0, okay. So this is the time, total time in a switching cycle for which we are going to use the vectors V1, V2 and V0, right? Now this T1, T2 and T0, so these are, so in a switching cycle in total time Ts, for example 100 microseconds, T1 is say 30 microsecond, T2 is 40 microsecond and T0 is 30 microsecond. Now in the total cycle, if the total amount of time is eaten up by T1, okay, so if I, so these are the basically the weights, okay, V1, V2 and V0. So if I use V1 for a large duration of time, the VR vector will move towards that. So suppose I use V1 for large duration of time, then my resultant vector will come here. On the other hand, in a switching cycle Ts, if I use V2 for a long duration of time, the vector will move here, the resultant vector, correct? And if I use V0 for long duration of time, the resultant vector will remain small in size, okay. So therefore you can see VR can be moved here, here or here, okay. VR can be moved this way or this way, okay, by adjusting that how much time we are going to spend on V1, V2 and V0, okay. So as if like these are three weights on the sides of a triangle, and these weights are basically the duty cycles. So these weights can be adjusted, so where is the resultant vector comes in this triangle, right? And this is given by this formula here, VR equal to V1 into T1 by Ts plus V2 into T2 plus Ts and V0 into T0 by Ts, right? So this is how it is done, right? And so for example, now what is V1? V1 is nothing but the 100 switching state combination, because if you recall, 100 produces this vector here. So if I use 100 switching combination with for T1 period, okay, I will be using this and then I will come here, okay, like that, okay. So V1 means if the 100 switching state, that means A phase upper switch, B phase lower switch, C phase lower switch. If we use that circuit for T1 period, then basically we are realizing V1 into T1, okay. Similarly, the V2 that is 110, V2 is 110, V2 is switched for T2 period, and V0 that is 000 and 111, these are switched for T0 period. And basically this T0 period is divided into two parts, right? T0 by 2 and T0 by 2. So this 000 and 111 are used for T01 and T07 time periods, okay. So this is how space vector PWM is done, right? We switch the three nearest vectors for time durations T1, T2 and T0, where the T0 part is split into two parts, the first 000 and the 111. Again, as I told you, this has been explained in details in the other course. I'm trying to be concise here in this course, and we are not going to talk about the sequence of switching and all in this course here. Okay, now the question is, what are the values of T1, T2 and T0? How do I know this one? Okay, as I understand, I can switch T1, T2, T0 and I can move the resultant space vector, basically the converter voltage space vector, I can move it, okay. By using T1, T2 and T0, I can make it rotate or increase and decrease in length. But the question is, what are their values, T1, T2 and T0? So that you can get from the triangle rule, okay. So suppose here you can see this is the OA. So what is OA? OA is the quantity which is produced when you multiply or when you switch V1 for T1 duration of time. Okay, V1 is used for T1 duration and the resultant volt second is given by OA. Okay, OA is the vector which is produced when you switch V1 into V1 for T1 time period. Similarly, if you switch V2 for T2 time period, then you produce this vector OB. Okay, OB is V2 into T2 and OA is V1 into T1. What is OC? OC is the resultant. Okay, this is the VR into TS time period. Okay, so in this triangle, as you can see here, OA, so this is this angle is theta, and this is where the VR is present. This is the angle theta, and therefore this angle is 120 degree or 2 pi by 3, and this angle is pi by 3 minus theta. Okay, so therefore V1 T1 by this angle, so A by sine A, B by sine B equal to C by sine C. So V2 by T2 by sine theta and VR TS by sine 2 pi by 3. Okay, so once you put this equation and start solving them, then you know what is the value of T1, T2 and T0, as you can see here. And what are these values? These are this value, this and this. Okay, so for an example, so this is the expression of T1, T2 and T0 if you want to if you want to realize the space vector. Okay, now one thing that you should note is that this the space vectors, when we said the radius of the hexagon, the radius of the hexagon is 2/3 VD. Okay, if you recall from a few slides, the radius of it is 2/3 VD, right? So suppose we take a condition, what happens at theta equal to 0 and VR equal to 2/3 VD. Okay, suppose you want to produce a resultant vector which is this way. Suppose you want to produce a resultant vector which is this. This is the resultant vector. Okay, what will be your values of T1, T2 and T0? Right, you can always use the formula, but it is very easy to understand that at theta equal to 0 and with this one, T1 must be equal to Ts. Okay, and T2 will be 0 and T0 will be 0, right? Because only if T1, so there you understand that if the T1 is the full TS period, okay, if T1 is the full TS period, then the resultant vector is perfectly aligned with V1, and and it has no component on the other vector. Okay, and similarly if T2 is equal to Ts and T1, so VR will be equal to 2/3 VD at an angle of pi by 3 if, okay, T1 equal to 0, T2 equal to Ts and T0 equal to 0. Okay, you can understand from it. So if now I give the whole weightage to T2, then the resultant vector will move on this here. The resultant vector will move on this one. Okay, so this is how we can actually manipulate or we can adjust the resultant vector. I can put the resultant vector any other place. For example, I can put the resultant vector here. Okay, and then accordingly I can choose what are the values of T1, T2 and T0. Okay, so therefore I can move or manipulate this resultant vector. So this is how space vector PWM is done. Okay, again, as I told you, usually the zero vectors are kept equal. This gives the best harmonic performance. So we make the two zero vectors T0 by 2 into T01 and T07. Okay, and we make it half-half. So beginning of the cycle and end of the cycle. But for other switching sequences, for example discontinuous PWM, the division is not equal. We are not going to talk about it much, and you can see this lecture, or you can see some papers. Okay, discontinuous PWM means okay, we will see it later, but discontinuous PWM means the modulating waveform will come like this. It is one way, it's a DPWM1, and then there is a DPWM2 like this, and there are other techniques. Okay, so let us not go into those details as of now. Okay, and we can use the discontinuous PWM to control the losses in the voltage source converter. But again, we are not going to details into that one in this course. Now, what is the maximum voltage obtained in space vector PWM? And this is where the benefit of space vector PWM becomes apparent. Okay, now, so what is the maximum voltage that we can get? Is we will get it when the radius, it is corresponding to the maximum inscribed circle inside the hexagon. Okay, and what is the radius of this inscribed circle? How much is it? Because this value is 2/3 VD. Okay, and therefore this length here, this length is 2/3 VD into cos 30 degree. Okay, and therefore it is equal to 0.577 VD. So the peak of the space vector the space vector amplitude is 0.577 VD is the maximum voltage that you can get. Okay, note that in sine PWM, okay, the peak AC voltage that was obtained was 0.5 VD. So from sine PWM, okay, we got 0.5 VD, which we said that m VD by 2. Remember, m VD by 2, and we are putting m equal to 1, and this will give us 0.5 VD. Okay, in sine PWM, whereas in space vector PWM we get 0.577 VD, which is basically 1.15 times VD by 2. Okay, so this is where the space vector PWM is like producing. So if you see here, there is 15% more. Okay, so which means, what does this mean? It means that when you use sine PWM, okay, this is where this sine PWM circle is also drawn. So when you use sine PWM, if you get X, suppose your DC link is VDC. Okay, if your DC link is VDC, this is your DC link voltage. Okay, the maximum peak AC voltage that you can get in sine PWM is VD by 2. Okay, peak AC voltage, RMS is VD by 2√2. Okay, in sine PWM. Whereas from the same VDC with space vector PWM, okay, you will get 0.577 VD. Okay, 0.57, so this is equal to 0.5 VD, and here you will get 0.577 VD. So you get actually 15% more. Okay, 15% more with the same DC link. Okay, with the same DC link, space vector PWM produces more AC voltage as compared to sine PWM. This is the biggest advantage of using space vector PWM. Okay, you get 15% more AC voltage, 15% more AC fundamental voltage. Okay, that we get from space vector PWM when we use as compared to sine PWM. Okay, yeah, that is what is written. Of course, the other benefit is that space vector can be modified to discontinuous PWM. You can adjust the T0 time periods unequally, and then you can clamp certain parts of the voltage waveform, which we are not going to discuss in this course, right? But it can be done. So there are several papers on that. Now, one of the things is that the SVPWM technique that we have discussed so far involves substantial calculation. Okay, as you can understand, sector identification, you have to identify which sector, then you have to do the timing calculation, you have to need to find out theta, okay, and then find out T1, T2 by using those trigonometric formulas, all those things. Okay, so that will require a lot of calculation, and it will burden unnecessarily the, say, digital signal processor or DSPs, which we are going to use for the space vector PWM. Fortunately, there is a technique in which we do not require any calculation, sector identification or switching sequence. Okay, it is not required, and space vector PWM can be easily done very quickly by adding a common mode voltage of triplet order to all the three modulating waveforms. Okay, it is very easy to actually implement in a digital signal processor if we can implement the signed PWM. And so we add a common mode voltage. Common mode voltage means a voltage which is common to all the three phases A, B, C. We add this common mode voltage to all the three phases, okay, and we will get space vector PWM automatically. What is the magnitude of this common mode voltage? The common mode voltage is given by this VCM equal to minus of Vmax plus Vmin by 2. Okay, and once we obtain the modulating waveforms from this, we add this VCM to all the modulating waveforms and space vector PWM will be realized. I'll show you how this common mode voltage look like from this waveform. Here you can see, first you see this is the original sine wave, the modulating waveform for sine PWM. Okay, and this VCM, this is the black color waveform, is the VCM, and this VCM is Vmax plus Vmin by 2, minus of Vmax plus Vmin by 2. What is this minus of Vmax plus Vmin? So at any instant of time, so let us take one instant, let us take one instant of time here. Okay, and here this is the maximum, this is the middle one, and this is the minimum. Okay, this is minimum and this is maximum at this time instant. Okay, how the common mode is generated? So VCM, as I told you, is equal to minus of Vmax plus Vmin by 2. When you do this calculation, then you get this common mode voltage, the value here. Okay, so at each instant of time, basically you find out of the three phases which one is the maximum, which one is the minimum, add them together and divide by 2 and this minus, and then it will give you the VCM, okay, the common mode voltage. This common mode voltage, whatever you have got, is shown by this black waveform. Okay, now you add this common mode voltage to all the three phases as a, so because it is a common mode voltage, you are going to add it. Once you add it, so then you get this waveform. Okay, VCM is added to the sine waves, and then you get this waveform here. Okay, this is the waveform you get. So this waveform is the waveform for space vector PWM. Okay, and this looks a little bit different from sine PWM, right? But it actually means this sine PWM plus the common mode voltage. Okay, you can do it yourself and we'll see that add the sine wave with this common mode and you get this voltage here. Okay, fine. Now this, with this waveform, you simply do a comparison with the triangle just like what you did in sine PWM. Okay, there is of course a high frequency triangular wave here. Okay, and you just simply turn on and off the switches. So with the logic that if the modulating wave is more than the triangular wave or the carrier wave, then you turn on the upper switch. If it is less than the triangular wave, then you turn on the lower switch. So with that simple logic and with this modulating waveform, so this is the modulating waveform. This is called the, these are the modulating waveform for the three phases. Okay. With these three modulating waveforms for the three phases, you just simply do the comparison and give it to the switch. You don't have to do any sector calculation, any timing calculation or theta calculation, nothing is required. Just add the common mode which we have obtained and add it to this waveform, whatever is there, add compared with the triangle, and you will get your PWM pulses. Okay, it is as simple as that. Okay, one thing that you note here, and this is where we must note it, and this gets interesting, is the fact that you see here, okay, here the sine wave we have drawn for m equal to 1, and here that's why it was touching this one line here. Okay, remember our triangles are always between +1 and -1. Okay, that is what we have assumed. Okay, so here in this, on the left side waveform, we have reached m equal to 1, so the sine wave at one point is touching m equal to 1. On the other hand, when you add the common mode, once you have added the common mode, what you see here is that the peak is no longer touching the one line. Here is the one line, 1 and -1. It is no longer touching. It has been actually subsided. It has reduced in its amplitude. Okay, how much is the reduction? In fact, this reduction is 15%. Okay, we actually reduce this one. So what does this mean? Okay, because of the addition of common mode voltage, the resultant waveform, which we are basically comparing for the triangle, the resultant amplitude has now gone down, and so it is now possible for us to increase the value of m to 1.15, as you can see here. Now m is increased to 1.15. Okay, it has gone more than 1, so you can see here this is 1 here, and now we have gone more than 1. Okay, so once you get to more than 1, and when you add the common mode, now you add the common mode to all the waveforms, then you see that it is touching 1 here. So it means that this is the reason why we got 15% more DC bus utilization, because as I told you, in order to prevent overmodulation, we don't want overmodulation, because overmodulation creates lower order harmonics. So we would like to be in the linear modulation. Linear modulation means that the carrier is between +1 and -1, and the modulating waveform is also between +1 and -1. But now we are basically able to go with the m equal to 1.15, which is more than what can be obtained in sine PWM. So in sine PWM, if we had used this one, we would have gone to overmodulation. Okay, here we are overmodulation in this case, but here in this case we are in linear modulation. Okay, so that is the 15% extra which we get in space vector PWM. Okay, and so here we show you some of the simulation waveforms. Okay, so here you can see, suppose we have used VDC equal to 600 volt. How much is the fundamental pole voltage when you use space vector PWM? We get this 1.154 times, basically this is 2/√3 actually. Okay, 1.154 into suppose the DC link is 600 volt, 0.5, so MVD into the modulation index is 0.98. Okay, so m is, in this case, m is equal to 0.98. Okay, so we get 339.27, which we can see here in the pole voltage. You see here the pole voltage is between 0 and 600. It is switching using the space vector PWM. Okay, the switching is done in such a way. This is the switching happening. okay, like this, okay, with the triangular wave which is very fast here, okay, and then you get the pole voltage. Of course you have a DC. The DC is because you are switching between 0 and 600, so there is a DC of 300 volts. There is a fundamental, and you see there are triplet harmonics. These triplet harmonics are coming because we have added the common mode voltage, okay, that the triplet order harmonics we have deliberately added to the modulating waveform. But since it is a common mode voltage, okay, so in the line voltage it will go away, right? The line voltages, in the line voltages you can see, now we have shown the line voltage, all these triplet order harmonics, they disappear. So there is no triplet order harmonics anymore, okay, because see in the line voltage VAB, we will be VAO plus VCM, and this will be VBO plus VCM, and so sorry, not this way, VBO plus VCM, okay, so this is how it looks like. So therefore the VCM and VCM, they actually get cancelled out here. So VAB in the line voltage, we do not get the common mode voltage anymore, okay. So therefore the common mode voltage or the triplet with which we are using in space vector PWM only comes in the pole voltage. It does not come in the line voltage, and therefore it will not appear in the line current also, right? And this is the this is not the pole voltage, so this is the phase voltage here. This is the phase voltage, okay. Phase voltage does not control, so the phase currents will not also have this harmonics, okay. Now space vectors can also be applied to unbalanced system, okay, as I told you, okay. So in case of unbalanced system, so when we have an unbalanced system, we actually can decompose into a positive sequence, negative sequence, and zero sequence components. As I told you, space vectors are generalized. So what happens then? The space vector becomes elliptical in nature. So I'll give you a small example. So as you can understand, any unbalanced system, suppose you have an unbalanced system, okay, so you have three sets of phasors then, okay. If this is a positive sequence component, okay, which rotates with the speed of omega, and so this is the positive sequence component. Then you have the negative sequence component, okay, and then you have the zero sequence components, okay, right? So this is the Fortescue transformation, and this one. Now suppose in many cases we don't suppose we don't take the zero sequence vector, because in isolated neutral systems the load current cannot have the zero sequence because of the isolated neutral. Suppose we take the simpler case, okay, where we have the positive sequence and negative sequence component. The positive sequence component basically will create a space vector, okay, which is like this, okay. The positive sequence is a balanced system and will create a positive sequence space vector. The negative sequence, this negative sequence will create another space vector which may be of different, this is also the same thing but which is rotating this way, right? But the diameter of the circle is different from the positive sequence diameter. So when you add these two, what happens is basically you have this vector rotating in this way, and you have this vector which is rotating in this way, okay. There are two vectors, there are two space vectors, okay, one due to positive sequence and one due to negative sequence, right? And so what is the resultant? So you will see, if you go on doing that, you will see that the resultant space vector is something like this. It becomes an elliptical space vector, okay. And when you add the zero sequence component, so this is a real part, and this is the imaginary part, okay, of the space vector. So when you have a zero sequence component, then the zero sequence component is on the axis which is perpendicular to both the real and imaginary, and it will become an ellipsoid. Okay, so it is a three-dimensional ellipse. Okay, so we generally call it as alpha, beta, gamma, but anyway, so yeah, so it becomes an ellipsoid. Okay, so this is a three-dimensional ellipse. Okay, right, so that is how the more generalized case of space vector when you have an unbalanced operation. But in many cases we have an isolated neutral, and we can see that the space vector is elliptical in the two-dimensional plane. Okay, so this is where an unbalanced operation can also be analyzed. Okay, with the positive sequence and negative sequence space vectors creating two circles, but having rotating in opposite direction and having different diameters of the two circles. Okay, we will quickly take up two examples very very quickly. So we can find out. So suppose we want to realize the space VR with SVPWM of a VSC. The following information is provided. The sampling time is this one. So this is TS 500 microsecond, VDC is 800 volt, VR is 400 volt, and these are the switching states. Okay, so basically we are here. Okay, sorry, 0 0 0 0 1 0. Okay, we are switching this and this, right? So therefore the space vector must be, resultant space vector must be here. Okay, active vectors timings are now we are saying that the active vectors timings are equal. So T1 is equal to T2. What does this information tell us? So first question, which sector the reference vector VR lies? Of course it is lying in sector 2, because we are switching 0 0 0 0 1 0. Okay, 0, this is 0 0 0 0 1 0 1 1 0 and 1 1 1. Okay, so therefore it must be lying in sector 2. Now the second question, what is the angle of the reference vector? Now here what I have given here is T1 is equal to T2. Immediately, if T1 is equal to T2, what does this mean? It means that this reference vector must be lying on this line. Okay, which is for this equilateral triangle, it is passing through the median of the equilateral triangle. So this reference vector will lie. So which means this angle must be 90 degree. Okay, so the answer is 90 degrees. What is the angle of the reference vector? Answer is 90 degrees. What is the time duration of the two zero vectors? Okay, how do I find it? Now we can do, what we can do is, we can do the volt second balance principle. So VR, we have found out, we don't know the magnitude, but we know the angle. So VR of an angle 90 degree into TS is 2/3 VDC, because this is 2/3 VDC, okay, at an angle of 60 degree, this vector, and this vector is 2/3 VDC at an angle of 120 degree. So 2/3 VDC of 60 degree used for T1 duration. This is used for T1 duration. This is used for T2 duration. Okay, so T2 and 2/3 VDC at an angle 120 degree. And so if you solve this one, you use the real and imaginary part, and you will immediately come out to be T1 and T2 equal to 216. And what is T0? T0 is T0 equal to TS minus T1 minus T2, which in this case TS is 500 microsecond and this is 216.5 microsecond, which will come out to be 67 microsecond. Okay, so this is how the three timings will be found out: T1, T2 and T0, which are used for switching the vectors 0 0 0, 0 1 0 and 1 1 0, as well as 1 1 1. Okay, take another example. Again here the very similar example, sampling time is 500, VDC is 500, and these states are used 0, 0, 0, 0, 0, 1, 0. So you can find out, so 0, 0, 0 is here, okay, and 0, 0, 1 is here, and 0, 1, 1 is here, and when I switch in a sampling, given T1 equal to T2 equal to T0, okay, T1 equal to T2 equal to T0. First question, what is the angle of the reference vector? So if these three T1, T2 and T0 are same, where will it lie? It is at the centroid of this triangle. So the reference vector must be here. Okay, because these are all equilateral triangles. So therefore, VR is at the centroid of the triangle. So therefore, obviously, this angle will be 210 degrees because this is like midway between 180 and 240 degrees. So this is 210 degrees. The magnitude of the resultant vector, how much is the magnitude? We have found out the angle. Now we can find out the magnitude. We can put it into this equation, okay, and can put again, so VR at an angle 210 degree and 2/3 VDC at an angle 180 degree into T1, and this one is T2, and then but T1 and T2 are equal. So given T1 and T2 equal to, and this will be must be equal to TS by 3, right? So therefore you can substitute T1 into TS by 3, T2 into TS by 3, and yes, find out, and you can substitute and then find out VR equal to 307.9 volt. So this value will be 307.9 at an angle of 210 degree. Okay, straight away you can find out. The other way of finding out is very also easy, that we can take this and do it geometrically. Basically you can, this is the triangle and we know the length of this triangle, okay, this angle is 2/3 VD here, 2/3 VD is there, and this is at the centroid, and you can find out what is the centroid of the equilateral triangle. Okay, you can find out what is the length of the centroid from the one of the vertex of the equilateral triangle from elementary geometry, and then also you will find out that the length of this vector is 2/3 VD. The length of the vector is 307.9 volt. Okay, you can do it also that way, also by using geometry. So with this two examples, we come to the conclusion of this part of the lecture, where we covered basic introduction to space vectors, a little bit of space vector PWM, and most importantly how space vector PWM can be used to control the converter output space vectors, converter output voltage space vector, and that converter output voltage space vector can be used or can be manipulated or can be adjusted to control the active and reactive power flow from the converter into the grid or vice versa. Okay, so basically we are adjusting. The main difference with the space vector approach and the phasor approach is, with phasors also we can do the same thing, but phasors are at steady state and space vectors are applicable both at steady state as well as transient state, even under unbalanced condition. So that is the main advantage of going into space vectors, and that is what we have covered in this lecture. Thank you.